Okay, so I'm going to make a start. So today we're picking up from where we left off on Monday, talking about the rest of object-oriented programming. And so on Monday we looked at how we can do inheritance, and we looked at vtables, and we finished off on Monday with a couple of vtable examples and issues to do with object slicing, and how we can overcome some problems to do with when code doesn't do what we expect it to do, particularly for name hiding problem. Now, we're going to just talk very quickly about covariance and contravariance, and this is more object-oriented programming ideas than strictly C++ ideas. But let's assume we have class B, which is a subtype of class A. So for instance, let's go back to our book example. We have class discounted book, which is a subtype of class book. Now, when we talk about covariance, this is an example of a covariance. So if we have a function, say the net price function that we had for discounted book and we had for book on Monday, what should the return type of that overriding function be? So all the return types of the overridden functions should return the same type or a narrower set of types as what the base class had. Okay, and this is said to be covariant. So what that means is, say we have the net price in we have the net price function on the class book, and we've got the net price function on class discounted book. The net price function on class book might return a double. The net price function on the discounted book might return some class that itself extends double and has a limited or smaller range. So say we might want a net price function that returns a double, and the double can't be more than value 100 or something like that. It's a bit of a contrived example, but the covariance whereabouts for return type is some value that's either the same or some limited subset of that previous value. You shouldn't have a situation about the return type for the net price inside the discounted book class is returning a string or a complex number or something like that. That's got no relation to the function it overridden. Contravariants apply to the parameters going in. So all member functions of B, so this is a bit of a bad example because A and B has been swapped around in comparison to base and inherited. But say all the member functions of the discounted book class must take the same or a broader set of arguments compared to member functions of A. And so this is basically the reverse of the covariance. So they've got to take the same arguments or a broader set of arguments. Okay. So the what's coming out of the functions, the return types need to be covariant. What's going in needs to be contravariant. What this means is you've got things like this. Okay. Here we have overridden virtual. Okay. So we've got this function A and this function, sorry, not function A, so we've got a function f and a function f that gets overridden, both are virtual. The signatures are the same, okay? The return type in A, this returns an A, and the return type in here, this returns a B. And so this is a covariant because the return type in this f function is a narrower set, okay? This is a narrower set, okay? So that's a covariant. You can do the same here. Say we have abstract base class called shape. Okay, it's abstract base class because everything's virtual and not defined at all, so everything's virtual equal to 0, abstract base class. We have a virtual void draw function, we have a virtual shape star clone function, and this clone function is going to, in a derived class or inherited class, provide some sort of cloning ability on this type. Now, we don't want to return strictly a shape star because that's an abstract base class. It can't be initialized itself. We want it to return the right type further down. Okay? And anything that inherits this class that actually wants to be turned into a class itself needs to provide a definition for this function because it's an abstract function up in the shape. So inside circle, the derived class here returns a circle star, which makes sense, and the square class down here returns a square star. Okay, and this is fine because these return types are covariants. Okay. And the question is down here, will contravariant return types work? They basically won't. Okay, so you need your return types to be covariant. Now, one of the other things that goes on, if we go back to Monday, that we should just clear up very quickly, is how the static and dynamic binding and compile time functionality works. So I have two classes here. Well, actually, they're structs, but the same thing. They're two classes. I've got class B, which is a base class, and struct D, which is the derived class. Okay. Both of these things have a function called foo. Both of these functions have a default argument going in. So up the top it's got I equals 1, and the second one's got I equals 2. Inside main, I create a new class of type D. Okay, so a new derived type. I then assign that to a pointer to B. That's fine because it's not object slicing. It's fine because it's a pointer, so that still works. And then I call P pointing to foo. Now, if you remember back to our V tables, despite this being a pointer to B, because it's really an object of D, in the V table for this function foo will get called, and so D will get printed out. Okay, D will get printed out. Now, we didn't pass any argument into this. Okay, so the default argument should come out. So we'd expect that to print out D2. That's what we expect to get printed out. The reality is D1 gets printed out. The reason why D1 gets printed out is because at compile time, it assumes that this call P pointing to foo, that this P is actually of type B. This type B up here is got the default value of 1, okay? And so that just substitutes in foo brackets 1 into there, okay? Because at compile time, the static binding goes on, okay? I can show you this live. I'll bring it up on my system. Just double check I've got the right code up. Yeah, I do. So I'm just going to bring this up on my system over here, okay? And so here's the code, default.cpp. I have my struct B. I have that exact same code on both screens. Okay, I'm not doing anything magic here. I'm now going to compile this. So G++ standard equals C++11 default.cpp. Okay, that goes and compiles. I run that, and there you go. Up the top of here, I get out D:1. Okay, so you've got two things going on there. You've got the static compile time going on, and so it's at the static level, of compile time level, that default argument, it assumes that this P over here is a B object. So that gets the equivalent call as if we'd stuck the value 1 inside there. At runtime, it gets dynamically bound and gets sorted out. Now, if in this code I change this B over here to be D, like that, and I recompile this, what's the output going to be? If I've changed the code to be that, what's the output going to be? D2. Should be D2? It's D2. Okay? So we've got a separation of what's going on at compile time and runtime. Okay? At compile time, it's going to assume all the time that this thing over here is actually a B object. At runtime, that dynamic binding goes on. Okay? So that contravariance and covariance stuff, that's quite complex. It's stuff to keep in the back of your mind. The reason why I went through that a little bit quickly is not actually strictly exam questions on that, but stuff to keep in the back of your mind if you're doing further stuff later on. This next section though is for important stuff for focusing on the exam. So we're going to go back and we're going to have our three classes again. We're going to have our class book, our discounted book, and our bulk discounted book. And so we've got class book is the base class, discounted book inherits from the base class book, and the bulk discounted book inherits from discounted book, which of course in turn inherits from book. And we had this image on Monday of the way in which these objects were set out of memory, so 1, 2, 3 in terms of them being set up like that. And within each sub-object from a class, okay, so a sub-object is just being what it wraps around or what it inherits from. The data members are initialized in declaration order. So that means that when we create a bulk discounted book, what we do is we first of all go and create a discounted book. When we create a discounted book, we first of all go off and create a base book, okay? So in memory, we've got this book, then the discounted book, and then the bulk discounted book in that particular order, okay? Destruction. For destructor, the reverse happens. The reverse happens. So for destructing this object, we first of all call the destructor on the bulk discounted book, for destructor then on the discounted book, and the destructor for the book, because the destruction process happens in reverse to the construction process. Okay? And so when we're laying this stuff out in code, the same as any other class that we've done for the rest of the semester, we have the member initialization list. Okay, and we've got to initialize stuff in the same way in which they're declared. Okay, and so when we're setting up a constructor like this, okay, we might have arguments coming in, and then we call, okay, so discounted book. First of all, we call the book constructor passing through those arguments as required, and then the additional values that we're putting on there. Okay, now, if the base constructor is not called by the programmer, okay? So say I did not put the call through to a discounted book, I didn't put the call through to the book constructor. If I didn't do that, okay, the compiler automatically does that for you, okay? But if there's no default constructor, so it automatically calls the default constructor, it doesn't know to pass through that data. If there's not a default constructor defined, it will scream. The compiler will scream, and the code won't compile. Okay? So when you're inheriting, you need to know the structure of the constructors of the things that you're inheriting from in order to construct your object correctly. And the same applies in the destruction process because it goes in reverse. Okay? So this is where some important stuff comes up. So constructors are not virtual. We went into that on Monday. Constructors are not virtual. The reason why constructors are not virtual is because it doesn't make sense for a constructor to be virtual, because an object isn't actually finished creation until the constructor finishes. So you should never have a constructor calls a member function. You should never have a constructor calls a member function. Okay? Sometimes people do. Actually, my solution to assignment 3 did, because my copy constructor called a function I'd written called copy graph. But it's not ideal to have a constructor call a member function, because the constructor, you should not assume it for objects fully constructed until the object returns, until the constructor returns. And so constructors definitely shouldn't be virtual, or cannot be virtual, because it doesn't make sense for that to happen. Because say we have a class, say we have a discounted book in our book class, both have got the function net price. If the constructor inside book called net price, if the constructor inside book called net price, then you don't know if it should call the net price of the discounted book, or if it should call the net price of the base book class. Okay, whereabouts if that object was fully constructed, even if you have a pointer to a book object, but the thing it's actually pointing to is a discounted book object, if you call it because of a v-table, I'll always call the discounted books objects net price function. Now we're going to go into that in an example in a few slides' time, okay? But keep in mind that as we go forward, okay? Constructors cannot be virtual. On the other hand, destructors must always be virtual. Constructors are never virtual, destructors must always be virtual, okay? and because of this, okay? If we have, again, this discounted book, okay, and we call delete P, this will call the destructor on discounted book. If we swapped out discounted book there for book, and we said delete P, because of dynamic binding, because the destructor is virtual, it will always call the destructor for discounted book. If the destructor is not virtual, and we say you discounted book, and we assign that to book star, okay, and we say delete P, and if the destructor is not virtual, because of static binding, it will call the destructor for book. And so the book component of discounted book will get destructed, but the rest of the discounted books objects will not get destructed. Okay, so the wrong destructor will get called. Okay, so your destructor must be virtual. Okay. Now, when you create a virtual destructor, though, okay, when you create a virtual destructor, you lose your automated move constructors and move assignment operators, okay? So when you've created a virtual destructor, because a destructor is part of a big five, you lose automatic compiler building of copy constructor and everything else. So you then must have to go and define your own. If you are satisfied that the ones that you're going to define for your own ones it should match up to what the compiler already has, you can just tell the compiler, actually go back and compile the ones that you would have normally compiled by going through and say equals default, like that. Okay, and we've already seen some of that code earlier on the semester as well. Okay, this is more important than any other code I've seen previously in the semester when it comes to this sort of putting back into place things that the compiler might not have generated because of inheritance. Because if you don't do this, then derived classes later down the chain might rely on stuff that should be there but it's not. Okay, so you've got to be think very carefully when you're building this sort of stuff. So here's a quiz. Okay. I have some code here. Okay, I've got class A, class B, and class C. Class A has a function called virtual void if, and that shouldn't say if and B, it should say if and A, okay? So imagine it says if and A. I have a void if, okay, and I don't strictly need to put the word virtual there, but maybe I want to. I could put the word virtual there as well. That says if and B, okay? And I have a void if up here in class C, which says if and C, okay? So all these if functions all overwrite each other, okay? I go and create a C object. I then assign that C object to a reference, and then I call a.f. Okay. And the question is, what's the output? Okay. If we go take a look, after I just went on a rant there and said that you shouldn't put function calls inside constructors or destructors, this is an example of if you do and what might actually go wrong. Okay, so this code is going to compile and it's going to run. Okay, but let's look at the case. First of all, if we call a.f. Okay, so we've got f and a, even though it says f and b, we've got f and a, f and b, f and c. Okay, if we call a.f, what should the output be? So this is the easy case. If we call a.f, what should the output be? If we call a.f, okay, and a is a reference to a C object, what should the output be? F and C. Who thinks it should be F and C? Who thinks it should be F and A? Okay, it's going to be F and C. Okay, it's going to be F and C because because this is a C object. Okay, so because that's a reference to A, hasn't been sliced, because it's a reference to A. Okay, it's going to take a look at the V table, the V pointer for the object C. Okay, and so it's going to print out F and C. Okay, so this a.f function is going to print out F and C. Okay, but that's not the complete question. Okay, the question said what's the output. So we go back to the start of main, and we said that we had this C object. Okay, now when we went to create the C object, we called class C. Okay, now class C doesn't have a constructor. Okay, so it's automatically going to be generated. That automatic constructor generation for class C is going to call for constructor for class B. We go into class B. Class B, what's the first thing that constructor is going to do?
It's going to call the function add.
No, something before that.
Oh, it's going to
What's the first thing that the constructor in class B is going to do?
super add.
Okay, it's not super, it's Java, okay, but same idea.
Yeah.
Okay, it's going to call for constructor for A. Okay, now we don't have a constructor for A, so once it's automatically generated, it does nothing. Okay, so first step, that called for constructor for A. Now it's going to call for function F.
It's a virtual case.
What function F is going to be called at this point? Is it going to be F and C? It's not going to be F and C because the C object hasn't been constructed. We've constructed A and we've constructed B. Okay? So the output is either going to be F and A or F and B. Okay? And in this case, it's actually going to be F and B because the rules for this, okay, which are actually written up the top of this, is if a member function is invoked inside a constructor or destructor, the version is invoked for one defined in the type of constructor of the destructor itself. So this is a B constructor and a B destructor. Okay, so F and B is going to be called, it's going to ignore the V table. Okay? So this is a special case. If for the case of A.F, okay, which you first discussed, the easy case, A.F, that's going to call F and C, but for constructor it's going to call F and B. Okay? So, we go back to the question, what's the output of this program? Who thinks the output of this program is F and B, F and C? Who thinks that's the output? Who thinks the output is F in, I don't know. Who thinks the output of the program is F and B, F and C, F and something else? Is there a third line of output of this program?
Yes.
Why is there a third line of output of this program?
Because of the destructor.
Because the destructor. So there is a third line. Okay. So the destructor is going to get called. And what's the output from the destructor?
From that line at the top of the slide, it's going to be F and B.
It's going to be F and B. So there's your construction of your objects. A gets constructed, B gets constructed. Okay. And so with your construction, B is the objects currently being constructed at that point, so F and B gets called. The same for destructure, and for destruction it works in reverse. C is already destructed by the time it gets into B's destructor, so F and B gets called. And so the output of this program is F and B, F and C, F and B. Okay, now I'm going to show you this running, so it's up on the screen here. Okay, this version does have F and A set up correctly. And so I go and compile that. Okay, and I run that, and there you go, F and B, F and C, F and B. Now, let's change this a little bit. I take out this void function here. I take out this F and B void function. Okay, so I've been left with F and A and F and C. What's the output?
Replace all F and B's with F and A's.
Okay, so you think it's going to be F and A, F and C, F and A. You think that's the output?
Yes.
Yep. Anyone agree? Yep. Let's take a look. Correct. Okay. Now, let's change this code just a little bit more. I have, instead of C like that, I have C is now a pointer equals to new C. Okay, and that's going to be equal to the dereference of that. Okay, this should recompile, just double check. It does. What is the output of this program? So you think it's going to be F and A, F and C, F and A? Yep. Who agrees? Nobody agrees.
I think I agree.
You think you agree? Anyone disagree? What does Sean think?
I agree.
You agree? I don't. Okay, let's just run it. We lost the line of output.
I don't know.
Why?
Because it's the memory that you have in tracking it.
Yep. The version before, everything was created on the stack. Main went out of scope for destructors got called. I'm leaking memory. It was a trick question, but it's something you should be aware of. Okay? Did anyone see memory leak? One person? Are you lying? No? So, yeah. Be aware of this. Okay? So, you've got a couple of things going on those slides. Okay? This is stuff, the reason why I'm focused on this question, this is very much the sort of questions that you should be focused on for the exam. Knowing your V-tables, knowing the order in which things are constructed, knowing when the destructors get called, and in fact the destructors don't get called, of course, if you have a memory leak. Those are things you should be, well, some of the areas and stuff that you should be focusing on for the exam. Okay? So, what we're going to do now, we've got about 20 minutes left. What we're going to do now is take a look at how we might build an object-oriented implementation of a stack class, okay? And so there's about 20 slides here, might be more than 20 slides. I'm probably not going to get through them all. I don't think I need to get through them all, because I think you guys can take a look at them in your own time later on, okay? But what we're going to do is we're going to build a stack class. Now, we've built a stack class a few times already over the last few weeks. We built unbounded stack class, and we might have at one point built a bounded stack class. What we're going to do is we're going to build both a bounded and an unbounded, and we're going to tie them together through an abstract base class. Okay, so here's my abstract base class. Okay, it looks like this. It's got a virtual destructor. Okay, it's got a virtual push function, a pop function, a top function, a const reference top function, an empty function, a fill function, and it's got a deleted assignment operator, which we'll come to. Okay. If you're thinking in Java, this is the equivalent of an interface. Okay, so this is an abstract base class. We cannot create an instantiation of this abstract base class because nothing is defined. We've got all these virtuals equal to 0 all over the place. Okay, so we cannot instantiate this stack class. Now, the reason why we delete the assignment equals operator, okay, and for the simple reason that it makes no sense to assign stack 1 equals to stack 2 if the implementations are different. So say we have got a bounded stack, okay, and we're going to get to here, but we're going to have a bounded stack that extends or inherits from stack. We're going to have an unbounded stack which extends or inherits from stack. Say we've got a function foo that takes in just the base class of a stack and the stack references. Saying S1 equals to S2 makes no sense because the implementation of these things are different. So deleting that assignment equals operator is important because it prevents situations where this doesn't work. Okay? So you just delete that operator and then you will get a compile time error because it's deleted, but it helps you not cause bugs in your code. Okay? Because otherwise this code might compile, might not compile, but at runtime or some other point in time, something will go wrong. Okay? So we have this abstract base class that sets up for interface for stack, and we've got a delete assignment equals operator. Now, here is our bounded stack. Okay? So our bounded stack is called B stack, it inherits from stack. It's bounded to, by default, a size of 10 items. Okay? It's got a copy constructor, it's got a destructor. This one does have for assignment equals operator defined, but only for other types of B stacks. Okay? It's got push, pop, top, and all that, which is for inherited stuff, and see how these things are virtual. They're inherited from stack. And it's got an unsigned value for what's the top of the stack and what's the size, and the pointer here to a stack. So basically this stack is set up so that each stack is just a value plus a pointer to the previous stack. Okay, so that's the way in which you can do a bounded stack. Okay, and for .cpp file, just goes and does that. I don't need to go into details about how that works, just trust me that it works. Okay, and you can download this code from the course website. And then some more implementation of it there. Okay, so now we get to an unbounded stack. Okay, so unbounded stack is called UB stack. It also inherits from the abstract base class of the stack. For unbounded stack, basically creates just a singularly linked list, and so it has a head which goes off to this class called node, which is a private inner class. And so basically this sets itself up a bit like a linked list, and we've already seen this earlier on the semester again, and so we just basically have a reference to the first node. When we go look at the details of how this works, each node just has a pointer to the next element, and so on and so forth. So when we pop, we just play around for pointers. Okay. Now we've already seen UB stack and we've already seen B stack already in class previously. This is just for object-oriented version of it, which inherits from the abstract base class. Why might you do this? For the simple reason that if you have some client code, you can write implementation independent code. Your client code can work on the abstract base class's interface. So here is some client code which basically takes in a stack, okay, so a pointer to a stack. Okay, so even though we can't instantiate a stack object by itself, we can still instantiate a pointer to a stack object, because a pointer and a stack object are two different things. So we cannot instantiate for abstract base class. We cannot create a version of something that's completely abstract, but we can create a pointer to something that is abstract. Okay, so we've got this function foo that goes and pushes 6771 onto the stack, pushes 1927 onto the stack, pops 1927 back off the stack, and then prints out the top, which is going to print out 6771. Okay? And so we don't care what the implementation of the push, pop, top, or even how this stuff is stored underneath. Okay? So our client code can go off and use this abstract base class, there's no issue at all. We can even do this. Now my example I'm going to bring up on the screen is ever so slightly different to what you see there, but it's the same idea. We can have a function called makeStack, and makeStack takes in a built-in which either makes a B stack, so bounded stack, or unbounded stack, okay, and leaks memory because they're never deleted, but it returns a pointer to a stack, okay? And there's a couple of other things to note, like this here. So say if we have these in two different files, okay? This file here that's using just for abstract base class, okay? We go and change one of our implementations of bounded stack or unbounded stack. We don't need to recompile this code. We don't need to recompile this code because this code does not rely on anything to do with the implementation of, it relies on the implementation to make it work, but it doesn't rely on the implementation or at this point because it's generic to the abstract base class. This code here, because it relies on both bstack and ubstack, calling those constructors, if bstack or ubstack changes, we need to go and recompile this piece of code. Okay? Now, what I've done is I've created a file called stack client. It actually just brings these two things together. Okay? Basically, it's what you just saw on those previous slides, is what you see here, with the addition that I'm using a thing called type ID to go and get me the name of underlying type to show you this is actually working how you expect it to. And I'm calling in my main make stack twice, once with false, once with true. Okay, and so I go and compile this. Okay, and Sean will help me out if I stuff up like I did this morning, because I forgot how to compile things. So I go and compile stack client, okay, and I also need to, of course, go and compile my bounded stack.cpp and my unbounded stack.cpp. Again, if I had a make file for this, I might create the bstack.o file, I might create the ubstack.o file and stackclient.o file and link them together. That would be a better compilation process. But I'm just going to do it in one line, and I can't spell, so that doesn't compile. Let's try that now. Okay, that compiles. And I run this program, and what I get out, if we go back to my source code, remember my source code is going to print out the top, and it's also going to print out, if I dereference the stack, what the type of the thing it dereferences to is. Okay, and so what I get is I get a UB stack and I get a stack, and they're both pointing or referencing the same value, which is 6771, because I created two of those things and push on two of those things. So that makes sense to everyone. Yep. Okay, so I have my implementation free code, which is up the top of here. Okay, this implementation free code does not care about the underlying data type. Does not care about whether this is a B stack or UB stack. What it cares about is the underlying abstract base class data structure. So if you look at my includes, okay, again, this is where some of your code is important. If I look at my includes, I'm including stack.hpp there, bstack.hpp, and ubstack.hpp. Now, if I go look at my stack.hpp, see, I've got the header guards up here, because I need to highlight this again for some people, okay? I've got the header guards here. The reason why the header guards are here, okay, is because, go back into stack.hpp, bstack.hpp there, hash includes the stack.hpp as well, and of course, ubstack.hpp hash includes stack.hpp. If in that one there, I take out the header guards, what's going to happen? If I take my header guards off stack.hpp and compile, and now I've only got one compilation line, what's going to happen? I'm going to get a multiple declaration error. At least I hope I'm going to. Oops. There you go. Redefinition of class stack. Okay. So again, assignment 3, quite a lot of people forgot the header guards. This is a very good example of why you need header guards. Okay? Because without the header guards, I'm redefining that stack, because that stack.hpp file is being included in bstack.hpp and ubstack.hpp. Okay? And see, I wouldn't need to worry about the header guards, except for then those header files are then being hash included into stack client.cpp. Okay? So header guards incredibly important, and people keep on forgetting them. Okay? So we've got the implementation free code, which is our stack based. We can make the two different types of stacks. That's fine. We're all happy. So, in talking about OO, or basically a summary of where we're at. Okay? So polymorphism and this dynamic binding is achieved with virtual functions. Okay? If something is virtual, we can dynamically bind. If it's not virtual, we have the static binding. Okay? A class with virtual functions is also said to be polymorphic. Okay? If it exhibits multiple behaviors due to the multiple implementation of the virtual functions of the derived classes. Okay? So our book and discounted book are polymorphic. Okay? Combining abstract base classes and dynamic binding to separate an application's interface from its implementation is very, very, very powerful. It means that we can write this implementation-free code, and people can go and write the underlying base classes underneath. Okay, so that's basically a summary of the key points of object-oriented code. Okay. Now, again, I've got 10 minutes. I'm going fast this lecture, but we're going to attempt to make it. Thinking about the copy control, thinking about the big five. So we've got for destructor, for constructor, assignment, move assignment. Those constructors are not virtual. The destructor basically has to be virtual. Okay. Now, you only need to provide these for your derived classes. Okay. And in general, you can use the automatic compiler ones, except for if you're using pointers. If you're using pointers, you generally need to provide your own copy constructors. The instant that you define your own virtual destructor, which you should be doing, but the instant you define your own virtual destructor, you are required to put in the copies and remove constructors, otherwise the compiler doesn't generate them for you. Okay? So, again, this is the summary of how the virtual destructors work. We saw this earlier with the delete. Okay, if the delete. So let's take a look at the virtual destructor for UBstack. Okay, must have got that up on the screen. Yep. If I go take a look at the virtual destructor for UBstack.cpp. There it is. Okay, so it causes delete here, sort of thing. Okay, if this function, this destructor for UBstack was not virtual. If it wasn't virtual, then instead of this UBstack destructor being called, okay, instead of that UBstack destructor being called, what would happen is the stack destructor was called. And what I mean by that is if I go back to, say, stack.hpp, if I take the destructor, the virtual off stack.hpp, two things. First of all, this is now no longer a abstract base class, okay? Because that destructor is now not virtual. If I recompile this, it should recompile fine. I run this, it appears to be running fine. Okay? But what's actually happening is this destructor here. Let me go and put an implementation. Send a C out. Hello. Okay, let me put that into there. Okay, and let me go put this into. Let's just do a new UBstack. Okay, so I make this virtual. Let's just show us. I make this virtual. Both of these are going to be called. Okay. Whoops. And I'm missing. String. Okay. And they didn't get called. They basically didn't get called because okay, because that's dumb. Oh, I could do that. What was the UBstack? UBstack's the false one. Okay, so auto p equals. Okay, so I'm going to create a pointer for that, and I'm going to delete p. Okay, just to make sure that actually gets deleted. What have I done wrong? Pardon? Foo. Oh, sorry. Yeah, I've got you. Yeah. So let's say make stack there. We then call foo on p. Okay. Okay, that runs. And so now I've got both of these functions being called. Okay. So can we see that? And let's clear this and show you again. So because it's virtual, I get both of those destructors being called. Okay. If this is not virtual, I recompile this. I run it. I only got the first one. I only got the stack.hpp one. And because this didn't delete anything, whereabouts for UBstack destructor when deleted this head, I have now leaked that memory. Okay? So I realise I'm pausing and emphasising this point quite heavily, but that destructor absolutely has to be virtual. Okay? Also, destructors cannot be pure virtual. Okay, so that's the last point on that slide. So you'll notice if I put this back to like this, all these other functions in this abstract base class were equal to 0. The destructor was not, okay, because you cannot have a pure virtual destructor. Okay, that's a minor technical point. The copy constructor for these classes doesn't work as we expect it to, for the same reasons that we've already seen way back when we did the construction of objects to start with. So we need to write our own decopy constructors. The same applies for both the bounded and the unbounded stack. The same applies for the assignment operators. So we're going to write our own custom versions of those. Okay. So basically that wraps us up for OO, and this basically wraps us up for the content that you guys need to have known for that exam. Okay. Next week on Monday, as I pointed out, on this Monday just gone, next week on Monday we're going to be looking at basically advanced topics, which is a little bit ironic given the name of the course being Advanced C++, but we're going to look at more practical what you can go and do, what you should be able to understand at this point. So we're actually going to take a look at the source code in the STL for how the weak pointer works in the STL source code. We're going to look at a couple of other interesting things like that. On Monday we also might talk a little bit about performance and how you can think about getting high-speed optimizations and stuff out of your code. We're also going to then on Thursday, Dave, who's one of the tutors, is going to give a short lecture about callbacks and some event-driven programming. And so next week is all about practical stuff that you can go and do other bits and pieces with. If we have time, Sean next week might give a bit of an introduction to the code base of RunSwift, which is for RoboCup SPL team, because their code has how many thousands of lines of code? Too many? Yeah, so they've got maybe 100,000 lines of code, and how do you manage that? How do you compile that when you've got heaps of different files? Actually, Dave's going to talk very briefly about CMake and build systems and how we can manage dependencies and stuff like that. Then, following Monday, so the Monday of week 13, we have a 2-hour revision lecture, okay? And so that will go into, again, looking at some of what sort of questions you can expect on the exam. We probably won't work through too many of them, but we'll look at questions like this one here. How would you actually sit down and work this one out, okay? So on that note, we are done for today. We'll see you on Monday.